Hi, welcome to the zeroth mini lesson where I want to talk about what is this class, what is thermophysics, sort of where does it sit in the context of all the physics that you know about. And so the simple thing to say is that PY 413 at NC State is your introduction to thermodynamics and statistical mechanics, and it's particularly aimed at physics majors. It's not only for physics majors, but it definitely emphasizes a physicsy perspective as compared to, say, an engineering perspective. Another important aspect of PY 413 is it's really the starting semester where you have really advanced physics coursework in most of your classes if you're a physics major. And so it's the semester where you start 400 level courses, so 413 being one, and most people taking 413 are taking 411 with it. And those are both really hard classes, and they're advanced classes. I guess another special thing about thermal physics is, at least when I teach it, it uses a special homework rubric that I mentioned briefly in the syllabus vlog from earlier. And so that's again, sort of an aspect of emphasizing professional communication and not sort of low-level problem solving. So here's a quote about statistical mechanics from a famous book called States of Matter by David Goodstein. Ludwig Boltzmann, who spent much of his life studying statistical mechanics, died in 1906 by his own hand. Paul Ehrenfest, carrying on the work, died similarly in 1933. Now, it is our turn to study statistical mechanics. So that's like the very first paragraph in the first chapter of this book. It's supposed to be a little bit funny, and if you're on social media, about every 6 months, some new physics professor discovers this quote and remarks on how hilarious it is. I think it's not very funny. I think it actually proves two things. Number one, depression is really common, and in any field, whether it's stat mech or whatever, you will find people who have been killed by depression. So this is a bit of a false premise that Goodstein is setting up here. Point number two is that Goodstein is, of course, a famous scientist who is not thinking carefully about the impact that their words might have on vulnerable people. That's a common thing. So we know more about mental health now, and we know that it's really common to struggle with depression, and it's also treatable. So if you're suffering from depression like Boltzmann and Ehrenfest and many, many, many other people, make sure you treat it. So if you've had 203 with me, you've seen this plot before, but now we're moving along the plot. This is where I try to place this course, PY 413, in the context of the other courses, the other lecture courses that you take at NC State. I leave the lab courses off because they're a little bit different. So on the y-axis, I plot what I call expert level performance expectations, which I guess is a fancy way to say difficulty. But I'm trying to be more clear about what I mean by difficulty. And then on the x-axis, I put time in the physics degree program. And so you start out with mechanics and E&M, and they're fairly gradual increase in difficulty. And you go to modern physics, and there's a little bit of a bump in difficulty. And I think, as I mentioned, if you took this class with me, there's some debate about how far up the jump the PY 203 class is. I mean, I think the truth is it depends on the topic. Some of the topics are up here, and some of the topics are down here. And so on average, PY 203 is sort of starting to ramp up in expert level performance expectations, but it's not overall a huge jump. And so my claim is that when you hit PY 413 and PY 411 at the same time, you've really jumped up by a huge amount in terms of what's expected of you in the class, right? And so it's really important that you are aware of this and you are thinking about, okay, if this graph is true, or even approximately true, it may well be that the things I was doing in my 200 level physics classes are not really going to get me through these 400 level classes. So I think you want to be aware of this jump and what it might mean for what you would have to do in terms of your approach to the course. What's difficult in 413? I definitely want to say there are very few plug and chug topics where you just sort of have a formula and you want to plug some numbers in. Mostly we'll be doing derivations of formulas where the point of the problem is to provide a logical explanation of the derivation of a formula and not necessarily just to have a formula. We do use this homework rubric that really asks you to focus on clear communication of your logic. That's sometimes difficult. It doesn't have to be, but it can be. We definitely do routine advanced math, much more so than in previous classes. So you'll be doing a lot of multivariable calculus. You'll be doing integration. You'll be doing probability and statistics all the time. And then the last one is harder to explain, but you'll probably see what I mean in a few lectures. Sometimes we make weird arguments in PY413 that take some time to appreciate. And I guess I want to make the case that this is a part of the course. It's not that you, the student, are not smart enough to appreciate the argument. It's also not that me, the teacher, is not good enough to properly explain the argument. It's neither of those things. It's that the argument itself is unusual and requires careful consideration. You'll see what I mean. My opinion about the 413, 411 course sequence is that in they're almost complements of one another. In 411, I think you have much harder math and very sort of involved, detailed problem solving, but the concepts in 411 are relatively easy to understand. In other words, you sort of feel like you always have some common sense to fall back on. In 413, the math is relatively easier. Right, we're going to be doing several variable calculus. We're going to be doing a little bit of a combinatorics, but for the most part, it's easier than 411. But then the concepts and the style of argumentation is where it's difficult. That's my opinion about it. So what is the point of this class? Now, our basic idea is we have, throughout most of our classes, focused on microscopic equations of motion. So in classical mechanics, we have Newton's second law. In quantum mechanics, we have the time-dependent Schrödinger equation. These are microscopic equations in that you're talking about, say, the trajectory of a single particle or the wave function of a single particle. And then most of our experiments that we do involve measurements of macroscopic properties. And so, for example, the pressure of a gas or the magnetization of a magnet. And the question is, can we derive measurable macroscopic properties, or equations of state if you want, from the microscopic equations of motion, right? I mean, the hope is that you can, and so then the question is, what do you do? Just turn the crank? And by that I mean, do you solve Newton's second law for every atom in a gas? And so think about, if you would do that, you have 10 to the 23rd vector versions of F equals ma that are all coupled together, of course. Each of the vector equations has 3 components. You're going to need some initial conditions. It's a mess, right? And an important point is that even if you could solve F equals ma for every atom in a gas, what would you do with the actual solution? It would be impossible to work with in any useful way. So the answer is no, you can't just turn the crank. You need to insert new ideas to bridge from the microscopic equations of motion to the macroscopic properties and equations of state that are typically seen in experiments, right? And I think it's important that this is not just trivial new ideas, but there are actually new assumptions that come in, new concepts, and of course new tools. And so in this class, we start on the macroscopic side with thermodynamics. And basically, thermodynamics is the macroscopic theory of how to specify the macroscopic state under various conditions. We use statistical mechanics to build the bridge. So statistical mechanics in PY 413 will start in chapter 2. All right. And now here's the interesting point. So in some ways, I'm just defining what we do in this class. I mean, PY 413 is really, really focused on the macroscopic world and the bridge provided by statistical mechanics. But here's an interesting point that I think sometimes people lose track of. In this class, we essentially don't work on this side of the flowchart, okay? We assume that the microscopic problem is done, that we've solved it, and we know everything about it, or let's say we know enough about it that we can apply our new statistical ideas, assumptions, concepts, and tools from statistical mechanics, right? And so it's important to me to make the point that these two things are distinct, right? That using statistical ideas sort of assumes that you have the pieces already from the microscopic equations. Now, you know, that may not always be true, or it may be only approximate, but it is sort of an assumption. Right, and so what I'm saying here is that since we've solved this problem, we already know how to specify the microstate. And so the microstate might be specified in a classical system by giving the position and velocity of all the particles that you would assume you get from solving Newton's equations. Alternately, if it's a quantum system, you would specify the microstate by telling the wave function for every particle in the system. But that's assumed to be known, so you would tell the wave function and the energy. So here's an analogy for what we're doing, and it's only an analogy, it's not perfect, but I think it tells you the spirit of what we're doing in statistical mechanics and in this class. So let's think about a math problem where our job is just to specify the geometric object known as the sphere. And so if you remember some math class, a sphere of radius r is the set of points x, y, z whose squared sum of the coordinates is less than or equal to r squared, right? So I wrote it in this little set notation right here. Set of x, y, z coordinates such that x squared plus y squared plus z squared is less than or equal to r squared. So that's the 3D volume that's a sphere. And so in this example, the analogy of a microstate is to just list all the points that satisfy that condition. And that is, of course, a ridiculous idea, right? There are an uncountable infinity of points satisfying those conditions. And even if you would somehow be willing to say, okay, let's just think of a discrete grid, it's still ridiculous. It's not how you would specify anything useful about a sphere. So instead, the analogy of a macrostate in the sphere is to just tell the volume of the sphere. And that would just be one number, right? And so we know the formula for the volume of a sphere is v equals 4/3 pi r cubed. And so that's the analogy of the macrostate of the sphere. Instead of an uncountably infinite list, you just tell one number. Oops. And so the analogy of statistical mechanics in this example is the triple integral that bridges us from the Cartesian coordinates to the volume formula, right? And so you basically can compute the volume by integrating dx, dy, dz over the whole coordinate system from 0 to r all around the sphere. So integrate integrate x between these square root limits, integrate y between these square root limits, and then finish up with z between minus r and r. And so this is the analogy to what we do in this class, right? We figure out what's the important macroscopic parameter we care about, and we find a way using the new concepts and tools of statistical mechanics to generate that macroscopic parameter from the known microstate of the system. So it's not going to always be a triple integral. Sometimes it will be something like an integral, you'll see, but it's some kind of measure that we apply to the microstate. So yeah, this is how it would appear in our flowchart. The macroscopic analogy is just the volume. Microscopic analogy is this set of all points, and then the statistical mechanics analogy is sort of asserting that you can compute this volume via a triple integral over the Cartesian coordinates. I mean, I think that's really interesting, and I think it's really important to emphasize that that bridge, that middle step, will involve new physics. I mean, okay, in terms of math, I think mathematicians would probably not be very interested in the idea that there's anything new in the bridge, but this is an analogy. In actual physics, the bridge involves fundamentally new physical concepts, not just mathematical machinery. So there's another really important, what's the word? I've lost my train of thought. I guess an important reason for being really interested in this class, and that is the arrow of time. So I want to imagine that we're going to do an experiment where we make a cell phone video of a ball starting from rest and then dropping to the ground. And the question I want to ask you is, how can a person watching the video be sure that the video is playing in the forward direction rather than the reverse? Can I try to play this video that I made in my front yard the other day? Watch this. That ball just dropped down. And you're 100% sure that that video was playing forward, right? Even if the sound was off and you couldn't hear people talking in normal English, right? You're sure that video is playing in the forward direction. And the reason is because you saw the ball fall and hit the ground and stop, right? And so in principle it falls and maybe it bounces a little bit and comes back down and comes to rest. And we're really sure that we would never see the reverse happen, where the ball's sitting at rest on the ground and suddenly pops up and falls back down and pops up again even higher. You would never see it. And so this is an example of the arrow of time. And this is fundamentally a thermodynamic / statistical mechanic fact. In particular, if I would do this experiment in my front yard and not let you see the ground, let me play it.
Filming.
Turn the sound off. I'm going to turn the sound off so you can't hear the plop. There's actually no way for you to tell whether that was playing forward or backward using physics, right? It could be just as well that the ball started out down here and somebody threw it upward with an initial speed such that it stopped at the top. There's no way to actually tell the difference. And so it's really interesting that in order to assess the directionality of time, you need to note this object, the ball, interacting with another object in a non-reversible way. Again, so that's fundamentally thermodynamics and statistical mechanics, and we're going to see how that comes about as we go through this course. Really beginning in chapter 2, we'll start to see where the arrow of time comes from. So this is so fundamental. It's like, you know, one of the things that's most apparent in your everyday life is this arrow of time, and fundamentally it does come from thermodynamics and statistical mechanics. In particular, what's happening here is that entropy is increasing as the ball interacts with all the molecules in the ground. And that's a fundamentally irreversible process. It's a fundamentally statistical process, and it comes about from the second law of thermodynamics. And that's what picture I drew here. I actually forgot I drew this picture, but the basic idea is that the probability that all these random motions would suddenly act in a concerted way to pop the ball up is statistically impossible. By contrast, the ball coming down and contributing something to the random motions of all the atoms in the ground is quite possible. And so there's this inherent asymmetry in the two processes, in that one increases entropy by transferring energy into these random motions, and the other, the improbable one, would decrease entropy by transferring it out. We're going to talk more and more about this. You're not really supposed to fully understand this now. I'm just trying to convince you how important this topic really is. So the basic idea is that in the microscopic equations of motion, there is no arrow of time. These things work either forward or backward in time. In macroscopic circumstances, when, say, a ball interacts with the ground, there's an obvious arrow of time that you see around you every day. And so something has happened in the bridge. It's so important. There's real new physics here that you need to explain nature. All right, so that's basically my introduction to the course. We'll start doing real sort of textbook guided content in the next mini lesson.